Moving along to our next factor. This is one that we've seen before, and so we're going to revisit it again and start seeing how some of these ideas that we're talking about find application in organic chemistry. So the next one is resonance stabilization of the conjugate base. So let's take a look at a pair of acids. So we'll look at this structure, which is phenol. And this one, which is cyclohexanol. And let's use a base. Remove a proton from each, and look at the conjugate bases. And again, we're doing that so that we can assess the stability of the conjugate base, of the conjugate bases, compare them to one another, figure out which one is more stable. That will be the weaker of the two, and it's going to correspond to the stronger acid. So remember that the whole purpose of looking at the conjugate bases is to assess acid strength. So removing a proton from phenol, is going to give us this conjugate base. And when we repeat that for cyclohexanol, we get this one. Okay, so as the title of this factor suggests, one of these is going to be stabilized by resonance, the other one not so much. And so what we recognize in the conjugate base of phenol is that we have the pattern of having an atom with a lone pair next to a double bond. And so we can start delocalizing electrons into the ring, like so. Now, as we've seen before, we have another such pattern right here. So we could continue, but we won't take the time to do that now. So we'll just say etc. So there are other resonance contributors here. In the conjugate base of cyclohexanol, by contrast, there is no resonance available. We can't apply any of our allowable resonance moves to this structure. So this one has no resonance, whereas up above, this one is stabilized by resonance. So remember, when a molecule or an ion exhibits resonance, it's typically more stable or lower in energy than we would expect. So this is the more stable of the two conjugate bases, Cb for conjugate base, because it's stabilized by resonance. So what we would be thinking in a case like this is that the more reasonable resonance contributors a base has, the more stable it is. Thus, the weaker it is and the stronger its conjugate acid will be. Let's write all of that out. The more reasonable resonance contributors a base has, the more stable it is. If it's more stable, that means it's a weaker base. So thus, the weaker it is, and the stronger its conjugate acid. Okay, so to go back up to our example here, the conjugate base of phenol is the more stable conjugate base compared to the conjugate base of cyclohexanol. So this one is the weaker base, whereas the conjugate base of phenol is the stronger base. making cyclohexanol the weaker acid and phenol the stronger acid. Now, cyclohexanol is an example of an alcohol. So ROH, this is ROH. Remember, when we took a proton off an alcohol, we got RO minus, which is an alkoxide ion. So the conjugate base of cyclohexanol is an example of an alkoxide ion. Okay, the next factor is called an inductive effect. Now, in order to understand this in the context of acids and bases, we need to understand it in general first. So we're just going to look at what is an inductive effect, look at some examples of that, think about all of the terms that we're going to come up with to describe inductive effects, and then we're going to go back and apply those to an acid-base situation. So first of all, where are we going to start with this? An inductive effect. It involves delocalization of electrons. So an inductive effect involves delocalization of electrons. What we saw with resonance is that resonance was also a delocalization of electrons, but it was occurring through a pi system. An inductive effect, by contrast, occurs through the sigma framework of molecules. So this occurs through sigma bonds, as opposed to resonance, which is through a pi system. An inductive effect can be stabilizing or destabilizing to the structure that it's occurring in. Okay, so those are things about inductive effects, but we haven't really answered what it is. And you can define it or describe it as a redistribution of charge caused by nearby charges. That's one way of looking at this. All right, let's look at an example. So let's say that we have 4 atoms. They're all bonded to each other in this way. And the first thing we want to do is suppose that Z is much more electronegative than Y. So let's say that Z, whatever that is the most electronegative element in this set of elements. So Z is much more electronegative than Y, and A and W also. So what does that mean? What that means is that the bond between Y and Z is a polar bond. It's a polar covalent bond, and the electron density is being drawn or pulled toward Z because it's more electronegative. So Z has a partial negative charge, and Y has a partial positive charge. So the consequence of that is that Y, because it has electron density being drawn away from it or pulled away from it by Z, is going to try to compensate for that by borrowing from the next atom down the chain, which is W. So Y is going to pull on the bond to W, and what that's going to do is set up partial positive charge on W as well. Now that partial positive charge wouldn't be there but for the fact that Z, being so electronegative, is pulling electron density toward itself. So you can think of this inductive effect kind of as a dipole whose effects are felt remotely, that is, away from where the dipole actually exists between Y and Z. So this example of an inductive effect we can think of as a dipole whose effects are felt remotely, so somewhere else in the molecule. Okay, let's look at another example of an inductive effect. Let's check out this. So we're going to draw a structure that you've seen a couple of times. It has a carbon with a positive charge, so this is called a carbocation. Now, as it turns out, let's focus on these methyl groups. Remember that a methyl group is just an example of what we call an alkyl group, so a little hydrocarbon fragment or piece. As it turns out, alkyl groups, like methyl groups or ethyl groups or so on, are what we call electron donating or electron releasing. So alkyl groups are electron donating or electron releasing groups. What that means is that they donate or release electron density toward another part of the molecule. Okay, so each of these alkyl groups is releasing electron density through the sigma bonds that join it to the carbon with a positive charge. That's helping to stabilize the structure. So the delocalization that results stabilizes the carbocation. So delocalization of electron density, which is in this case occurring through the sigma bonds, stabilizes this carbocation. Now let's compare that to this structure. So let's say we have, it's going to be very similar looking. We'll have a carbocation, but instead of CH3 groups, we're going to have CF3 groups. Now the one that's at the top of the structure, I'm going to draw everything out. So all the fluorines, all the bonds to the fluorines, and all the lone pairs on the fluorines. Now, a little while ago, we remembered the fact that fluorine is the most electronegative element. So what that means is that in each of these carbon-fluorine bonds, you have dipoles because each of the fluorines is pulling electron density toward itself. So each of the fluorines has a partial negative charge, and that carbon, because it's having electron density pulled away from it by those 3 fluorine atoms, has a significant amount of partial positive charge. Let's call it partial plus plus plus. That's not really a thing. You're not going to see partial charges denoted with more than 1 plus. But I'm putting that there to emphasize the fact that a lot of electron density is being pulled away from that carbon. So let's take a look at where that carbon is, because that carbon is in the same situation as these other 2 carbons. All of them have significant partial positive charge. Well, they're right next door to a carbon that has a full positive charge. So the juxtaposition of a partial positive charge with a full positive charge is destabilizing. So a question that we might ask is inductive withdrawal, or is an inductive effect, always stabilizing? And the answer is no. In this case, the inductive effect is destabilizing. Because what it does is set up an area of partial positive charge right next to an area of positive charge. Having like charges next to each other, a full positive charge with a partial or full positive charge is destabilizing. So having like charges, that is the same charges adjacent to each other, is destabilizing because of the repulsion of like charges. Okay, let's take a look now at an inductive effect in the context of an acid-base argument. We're going to compare two acids. So this one, which is ethanol. Ethanol has a pKa of 16. We're going to compare that to this guy. So instead of the methyl group on the left side, we now have a CF3 group, or a trifluoromethyl group. This is called trifluoroethanol, and it has a pKa of 11.3. So again, we know the bottom line. We know that the trifluoroethanol is the stronger acid because it has the lower pKa. Now let's look at the conjugate base argument so we can see why that is. So this is the stronger acid. And because it's the stronger acid, that must mean that its conjugate base is weaker and more stable than the conjugate base of ethanol. So let's draw both conjugate bases. Now what I'm going to do is, just to remind you, I'm just going to draw the mechanism once to remind you how we get to the conjugate base, because you're going to be doing this over and over again. And so in both cases, what we're going to do is generate a conjugate base structure. So there's the conjugate base of ethanol. Now that's the conjugate base of an alcohol. This one is an alkoxide ion. And specifically, this one is ethoxide ion. Okay, so we have that guy, and now let's draw the conjugate base of trifluoroethanol. And that looks like this. All right, so what's going on in each of these structures? So first off, let's look at what's the same in each structure. In each structure, we have an oxygen with a negative charge that's bonded to a carbon. So you're going to have a dipole. So they both have that dipole, which is the same in both structures, so that's going to be a wash. So we have to look at what's going on with other things. Okay, so each of these carbons, though, has a partial positive charge. Okay, now in the structure on the right, the conjugate base of trifluoroethanol, we have a similar situation to what we saw in the previous example, which is that the fluorines are pulling electron density away from that carbon. That leaves the carbon with a significant amount of partial positive charge. So move this dipole over. So let's say partial plus plus plus. So a lot of electron density being pulled away from it. Okay, so what's it going to do? As we saw on the previous page, it's going to borrow from the carbon next door to it. So it's going to pull electron density this way. What's that going to do to this partial positive charge? It's going to increase it because now that carbon, the one attached to the oxygen, is having electron density pulled away from it in two directions. So let's say we'll call that partial plus plus. Okay, so what we have going on here is the following. Let's think about this just in terms of blobs of charge. So we have an area of increased partial positive charge right next to an atom that has negative charge. So an area of increased partial positive charge next to a negative charge. What that sets up is having adjacent opposite charges. That's stabilizing. Unlike having adjacent like charges, having opposite charges right next to each other, they attract each other. That lowers the energy of the system. So this is a stabilizing factor. What we could say here, because the whole thing started with those fluorines pulling electron density toward themselves. So a fluorine is an example of what we would call an electron withdrawing group. So an electron withdrawing group, which pulls electron density toward itself away from some other point in the molecule. Notice that none of this is happening in the other structure. So it's only by virtue of the presence of the fluorines that the carbon that's bonded to the oxygen has more partial positive charge character and thus provides more stabilization for the negative charge on the oxygen. So what we would say, the way we would describe this, would be to say that the conjugate base of trifluoroethanol is stabilized by inductive withdrawal of electron density. So because it's more stabilized, it's a weaker base than the ethoxide ion to the left, therefore corresponding to the stronger acid. Let's go back to the other page and take a look again at the examples that we worked through originally. Okay, so these two examples, the two carbocations. So in the first example, the carbocation is stabled by an inductive donation of electron density. And in the second example, the carbocation is destabilized by an inductive withdrawal. So you have inductive donation possible and you have inductive withdrawal possible, and either one of them can be stabilizing or destabilizing. So what you need to do is when you're assessing inductive effects within a structure, what you want to do is see how those inductive effects affect, for better or worse, any full charges you have in the molecule. So for example, with the carbocations, we look to see how the inductive effects affected the positive charge. In the example, in the acid-base example that we did on the next page, we looked at how the inductive effects affected the negative charge. Okay, did it help stabilize it, or did it contribute to destabilizing it? Let's look at some more ideas relating to the inductive effect. Okay, so let's say that we have CF3CH2OH, so trifluoroethanol, and now we'll compare that to CCl3CH2OH, which is trichloroethanol. So which of these will be the stronger acid? You'd be right if you said that it was the one with the fluorines. So if we extrapolate what's going on here to the structures that we drew above, imagine the structure of the conjugate base of trifluoroethanol, except replace all of the fluorines with chlorine atoms. So we can just draw that out quickly. So it'll look something like this. Like so. Let's clean up our bonds a little bit. I want to set a good example so that you get into the habit of drawing your structures as nicely as you can. Anyway, chlorine is less electronegative than fluorine. So although it's pulling on its bonds to carbon, it's not doing so to the same extent that the fluorines would, which means that the carbon attached to the chlorines, maybe we could say that this is just partial plus plus. So it's going to borrow less from the carbon next door to it, which is going to have a smaller effect on the carbon bonded to the oxygen. Another thing about the inductive effect is that it drops off pretty quickly after a couple of bonds. Let's take a look. So we have these three structures. Now remember, what we like to do is look at their conjugate bases. So let's go ahead and clean up this bond. Let's go ahead and draw the conjugate bases. And I'm recognizing that I left off lone pairs on the structures up above. And so because I want you to be putting those on, I better do that too. So let me go back and pop in all the lone pairs. Okay, so there's one of the conjugate bases. Now let's finish up and draw the other ones. Okay, so our assessment is, which is the strongest acid? Of these three, and as such, what we would need to do is draw their conjugate bases. All right, so let's take a look at each of these pictures. Now, they all have one thing in common, and that is this structural motif. In the carboxylate, remember that you have a resonance argument. So that's going to be true for all three of these. Now, you also have this going on. So there's a dipole here, and of course there's a dipole here as well. But what the dipole in the carbonyl in that structure shows us is that electron density is being pulled away from the carbonyl carbon. That sets up an area of positive charge that's directly adjacent to the oxygen that has the negative charge. That would be an inductive effect. So a carboxylate is stabilized by both resonance and an inductive effect. So resonance and inductive effects are at play. Okay, so what's different about the structures? Well, they all have the same number of carbon atoms. They all have 4 carbon atoms. So what's different about them is the placement of the fluorine in all cases. So the fluorine, wherever it's attached, is going to be pulling electron density away from itself. That last dipole really went off the rails, so let's fix that. Better? Okay, so the fluorine is going to be pulling electron density away. In the first case, that sets up partial positive charge here, and so that guy can borrow from the carbon next door, which is right next to the oxygen with a negative charge. So that's an effect that's going to be felt fairly strongly. In the next case, sure, you have partial positive charge on that carbon. It's going to borrow from this carbon, but then the effect is going to drop off fairly quickly. So there is going to be a little bit of borrowing here, but it's not going to be very much. And then finally, in the last example, that fluorine is far enough away that the borrowing kind of drops off by the time you get to the carbonyl. So the inductive effect isn't felt at all. So the inductive effect drops off after about 2 bonds. So what this means is that it's the base on the far left that's the most stable. So this is most stabilized by the combination of resonance and inductive effects because the fluorine is closest in. That makes it the weakest of the three bases. The one on the right is the strongest base. And so to apply that logic to the acids that we started with, the acid on the left is the strongest one, and on the far right is the weakest. Okay, so let's take a look at one more factor that we need to consider when we're assessing acid strength, and then we're going to look at a couple of examples. Okay, so charge is the last effect that we're going to talk about, and the charge that we're talking about here is positive charge. So if we're comparing two acids where the protons are attached to the same atom, and one of the acids has a positive charge on that atom, it's the one with the positive charge that's going to be more acidic. This one is actually going to be, I think, pretty easy for you guys to remember because you already know this comparison. So water and hydronium. So in each case, the hydrogen that could be donated to a base is attached to an oxygen. But in hydronium, the oxygen has a positive charge. We already know that hydronium ion is a strong acid and that water is a weak acid. But if we approach this using a conjugate base standpoint, the conjugate base of water is hydroxide, and the conjugate base of hydronium is water. Well, hydroxide has a charge, but water doesn't. So a charged conjugate base, this one has a negative charge, a charged conjugate base is less stable than a neutral molecule. So hydronium has a more stable conjugate base than does water. Let's look at another pair of examples for this. Let's take a look at ammonia, oops, not water, and ammonium. Okay, so once again, it's going to be the one that has the positive charge that's stronger. Notice that what we're looking at, though, is where the protons are attached to the same element. So we can't compare apples to oranges. Let's look at one more example. Okay. The thing on the far right is an alcohol, and this one is called tert-butyl alcohol. So tert-butyl alcohol. The thing on the left is tert-butyl alcohol after we've protonated it. So this is ROH2+. Now remember what we said about ROH2+ back a few pages ago. We said that it was a strong acid. We also know that alcohols are weak acids. So we could rationalize the difference in acidity that way. We can also apply the fact that a proton attached to an element with a positive charge is going to be a more acidic proton than a proton attached to the same element without the positive charge. Okay, so let's take a few minutes and just look at a couple of examples. So first of all, when you're assessing a pair of acids or a set of acids, the first thing you want to ask is, are the hydrogens that I'm comparing, the acidic or the potentially acidic protons, are they attached to the same element? If the answer is yes, then the factors you would need to consider would be, is there resonance stabilization in the conjugate base? What's the hybridization? What kind of hybrid orbital is the lone pair contained in the conjugate base? Do you need to consider the positive charge effect? Is either of the acids positively charged? And finally, are there any inductive effects that would affect the negative charge that you get in your conjugate base? If the hydrogens are attached to different elements, then the factors you would consider would either be electronegativity, if those two elements are in the same period, or size and polarizability, if the two elements are in the same group. What we've done through the packet, or through the last part of the packet rather, was to look at bases and assess base strength, and by doing that, we got into acid strength. So what this means is that with the tools that you now have, you can answer questions not only about acids, but about bases as well, because that's really what we've been doing. So let's answer this question. Which of these two is the stronger base? So we're going to compare the amide ion and this guy, CH3O minus, so that is RO minus, so this is an alkoxide ion. This one is called methoxide. So yet another example of an alkoxide ion. Okay, so amide versus methoxide. All right, there's two arguments you could come up with for this. So take a few minutes, pause the video, take a few minutes, and see if you can come up with at least one argument to support your answer to the question, which is the stronger base? Okay, so having done that, the two things you could do are the following. First of all, you actually happen to know the pKa's of both conjugate acids. So you could look at those. So NH3 and CH3OH. NH3 is ammonia, so it has a pKa of 36. CH3OH is an alcohol, so its pKa is going to be in the range of 15 to 18. That makes ammonia the weaker acid of the two acids, meaning that the amide ion is the stronger base. So that's one way you could answer the question. Another way to answer the question would be to apply some conceptual reasoning. So we would think about electronegativity in this case, because the negative charge is on a different element in each of the bases. In one case, it's on the nitrogen, in the other, it's on an oxygen. So those are in the same period, so we would think about electronegativity. And what we would think is that oxygen is more electronegative than nitrogen, which means that it's holding its electrons more closely to its nucleus. Those electrons are therefore more stable, which means that the base is more stable and less likely to accept a proton. So making the base more stable which makes it a weaker base, so less likely to accept a proton, or less able to accept a proton. Making methoxide the weaker base. So that's how you would reason your way into the answer. Now, throughout these factors that we've been talking about, I mentioned that you can use these arguments to compare two acids or to compare two protons within the same molecule. So that's what we're going to do now. We're going to look at a molecule that has more than one set of protons, and we're going to figure out which of those sets of protons is most acidic. So I'm going to put some labels on this structure, A, B, and C, and those relate to sets of protons. So on the carbon that I've labeled A, there's 3 protons. The same is true for C. The carbon labeled B has 2 protons. So the question that we ask here is, which set of protons is most acidic? Now, just because these protons are in the same molecule, nothing really changes. We're going to do the same thing, which is we're going to look at the structures of the conjugate bases that we would get by removing a proton from each of these sites. Now, before we start pulling protons off, let's recognize the fact that by symmetry, the A protons and the C protons are in what we would call the same environment. So they're going to behave exactly the same. So if we take a proton off of A, that's going to have the same effect as if we took a proton off of C. So let's take a proton off of A and draw the conjugate base that we would get. And so that's going to represent, we'll say, the AC protons. And then let's do the same, only with the protons attached to the carbon labeled B. So let's use a base and pull this guy off. Notice that the arrow is pointing directly to the carbon atom. Again, you want to be super precise with how you're drawing these arrows. It's one of the many things that organic chemists are super picky about, so be really attentive to that. Okay, so here we have our 2 conjugate base structures. Pause the video and analyze each one to see if you can come up with some reasoning. Okay, so once you've done that, I'd like to think that you came up with some of these ideas. So first of all, in the structure on the top, we have resonance delocalization. So the negative charge that starts out on the carbon, we can draw another resonance contributor that puts that negative charge on the oxygen. So it's being shared. There's also an inductive effect that's going on here. So there's a dipole between the carbon and the oxygen that's setting up partial positive charge on the carbonyl. So this is stabilized kind of like a carboxylate in the same way through a combination of resonance and inductive effects. Okay, now let's look at structure B. Well, structure B has got 2 inductive effects at play. So that negative charge in the center of the structure is flanked by 2 partially positively charged carbons, the carbonyl carbons. So that's an inductive effect, but you also have resonance. So you can start by drawing this resonance contributor. but we just as easily could have delocalized that charge to the other oxygen. So now let's take this structure and delocalize the charge to the other oxygen. Like so. Okay, so the bottom line here is that B, the conjugate base of the B protons, is more stabilized than the conjugate base of AC. It has more inductive stabilization. And it has more reasonable resonance contributors. Reasonable, meaning you don't want to count the super minor ones. Okay, so the original question was which set of protons is most acidic? When you pull off the proton on B, you get a more stable conjugate base than you get when you pull a proton off of A or C. So the conjugate base of B is weaker, thus the protons attached at B are stronger, or more acidic rather. So the answer would be the B protons. So you can use these factors not only to compare two separate acids, but to compare two sets of acidic protons that are in the same molecule.